Okay, in this presentation we are going to look at the log normal distribution. So here is a worked example. Suppose that we are considering the lifetime of batteries. Suppose the time in hours that it takes for a certain type of battery to fail. This will follow a log normal distribution with parameters mu equal to 2 and sigma equal to 0.5. So you probably recognize that this might be something to do with the normal distribution, and in fact it will be very closely related to the normal distribution in terms of the skills required. And we have mu equal to 2 and sigma equal to 0.5. Now those actually will equate later on to the normal mean and the normal standard deviation, but here they are just the parameters of the log normal distribution. So the exercises are as follows. Find the probability that a battery lasts more than 10 hours and calculate the mean and the variance of the battery life. So that is part A and part B. Okay, so let's look at exercise A. Calculate the probability that a battery will last more than 10 hours. So let x be the random variable representing the battery life. Okay, since x follows a log normal distribution, log of x follows a normal distribution with mean mu equal to 2 and standard deviation equal to 0.5. And crucially, that's an important thing there. So essentially, all of the skills that you should have built up by now regarding the normal distribution now come into play. And essentially, really, we're just actually making one more extension to it, one more elaboration to it. We're using the laws of logarithms and also sort of, in a way, exponentials. Okay, so to find the probability of x greater than 10, what we must do is convert this to the normal distribution. Okay, so the probability of x greater than 10, when we're looking at the x, the underlying variable, this is equivalent to saying that we're interested in the probability of the log of x being greater than the log of 10. Okay, so there's a direct logarithmic equivalence on both sides of that inequality. Okay, so first what we have to do is calculate the log of 10, and that turns out to be 2.3026. And now what we're going to do, so essentially if x equals 10, the log of x, the log of 10 is 2.3. So essentially what we have to do is find the z-score corresponding to 2.3, look it up in the tables or whatever approach we're going to look at how to calculate the corresponding probability. So now standardize this value using the normal distribution parameter. So this is straightforward z-score type stuff. The standardized value is log of 10 minus mu divided by sigma. Okay, so that is equal to 2.3026 minus 2, which is the normal mean, divided by 0.5, the normal standard deviation. So we end up with 0.3026 divided by 0.5, and that works out to be 0.6052. Okay, so that is the z-score essentially. But how do we work with that? Essentially the same sort of rules we would use for the normal distribution. In this case it will be the complement rule, etc. Use the standard normal tables, find the probability that z is greater than 0.6052. Now if you're using statistical tables like Murdoch-Barnes, you probably would just round that to 2 decimal places, 0.61. But if you're using statistical software like R, you probably just work away as is. Okay, so that's why I'm sort of be very approximate about it. You might have to round your z-score to 2 decimal places, and you probably go from 0.61. But anyway, I'll just keep going as is. The probability of z being greater than 0.6052 is, using the complement rule, 1 minus the probability of z being less than or equal to 0.6052, and that should get you a value approximately around 1 minus 0.7274. So you should get a number around 72% when you get here, and the complement of that is 27.26%, 0.2726. So therefore, the probability that a battery lasts more than 10 hours is approximately 0.2726. Now, moving on to part B. So calculate the mean and the variance. Now essentially what we're going to do here is use the formulae for the log normal distribution. Okay, so with parameters mu and sigma, the mean of x, the e of x, is given by this equation here. The expected value of x equals the exponential of mu plus sigma squared divided by 2. Now, just as a quick remark, usually you write exponentials as e to the power of something, but I've actually used a slightly different notation here because it just makes it easier to read. Okay, so the exponential of mu plus sigma squared over 2 is the exponential of 2 plus 0.5 squared divided by 2. 0.5 squared is 0.25, and when you divide that by 2, you get 0.125. So we're looking for the exponential of 2.125, which is approximately 8.372 hours. So moving on to the variance, the last part, the variance of x is given by this expression here. So just watch out for the different situations with regard to brackets and the different situations with regard to the exponential. The first part is the exponential of sigma squared minus 1. So you evaluate the exponential of sigma squared, so you evaluate that, then subtract 1. Okay, that's the first term. The second term is the exponential of 2 mu plus sigma squared. So you just actually calculate the 2 mu plus sigma squared and then get the exponential of the whole thing. So we end up with the exponential of 0.25 minus 1 times the exponential of 4.25. Okay, 2 times 2 plus 0.25, that gives you 4.25. So a little bit of calculator work. The exponential of 0.25 is 1.284. The exponential of 4.25 is 70.105. So just add them, combine all these numbers. So we have the exponential of 0.25 minus 1. That gives us 0.284 times 70.105. That's approximately 19.91 hours squared. So that is our variance. Okay, so I think that's us done for this one. I like the exponential. I like the log normal distribution. There you go. It's a bit of fun. Okay, we'll leave it there.